Hello, this video will look at quadratic models or applications of quadratic models. As it says here, in this exercise we'll look at applying our knowledge of turning points, intercepts and generating equations to help us solve worded style problems or real life problems. These generally feel tricky or confusing. But ultimately, all the questions that you'll come across in this exercise are questions to deal with quadratics that may or may not be disguised in some way. Sometimes they'll give you straight up front the quadratic, especially if it's a tech active question. Other times you need to apply knowledge of other topics and areas. So this is this idea of interrelated topics in mathematics, not just isolated standalone islands. You need to use maybe information from measurement or geometry or trigonometry. Somehow we end up building a quadratic equation. And then once we have the quadratic equation, you then need to use that to identify some information. Generally, what's the peak, the turning point? When does the golf ball hit the ground again? The x-intercept. So it's about interpreting how the quadratic equation, and if we graphed it, how it would relate to the real world situation. The easier questions, as it says, the equation is given to you. Generally, I suggest if it's CAS active, is just graph it, put it straight in your calculator and graph it so you get an idea of the shape. Otherwise, do a rough sketch so you can imagine the situation. So if it's quick to find, say, the intercepts or the turning point, and quickly find that so you get a rough idea of what the situation may be. And if the question doesn't give you defined variables, then you must define them yourself. You must give the examiner idea or tell them what the variables that you're using mean. While it's generally safe to assume what x and y are, you need to define them, how it relates to the real world situation. Okay, so let's get going and have a go. So we're just going to roll through an example of how we're not given a quadratic, but where a quadratic eventually appears, and then how we use that quadratic, how we can interpret that. A piece of wire 68 centimeters in length is bent into a rectangle. Let W be the width of the rectangle. So draw the above rectangle and label all information. So we're given a variable. So we can use that. We don't need to define anything else at the moment. So we've got some rectangle, and I know that's the width. I may as well call that L, okay, for the length, and we know the perimeter, okay, is equal to 68. Perimeter, just as a reminder, is the distance going all the way round, so we can also know that perimeter is equal to this over here's the width, that's over the width. It is width plus length plus length is for a rectangle 2W plus L. Write an expression for the length of the rectangle in terms of W. So when we have something that says in terms of, means L in terms of W means L equals something that has W in it. Okay? In terms of W means an equation that uses W. And this prior information that I've put up here, and I tell you, very common for these questions to use perimeter in some way and relate them perimeter to area. So being freshening up on perimeter of certain shapes and area of certain shapes will certainly be helpful. Right, so we have perimeter is 2W plus 2L, but we now want to write an equation L in terms of W. We're going to use this information here. The perimeter is equal to 68, and it's also equal to 2W plus 2L. So we know, right, but we don't know, but we can write that 28 is equal to 2W plus 2L. And we can just start rearranging this to try and get L by itself. So we 2L to, might start it the other way around. W 68, we get 2L is 68 minus W. and we get L is equal to 68. Take 2W divided by 2. We now have an equation, L equals 28 minus 2W divided by 2, that shows us the relationship between length and W, and it's L in terms of. I could, if you noticed, sorry, my we could simplify this though, take 2 out of the common factor of the numerator, so we get L equal to 34 minus W all divided by 2. Therefore we can cancel the 2 and the 2. So we get length is equal to 34 minus W. Either way, you had this answer on the left or this answer on the right. That's complete. Write an expression for the area of the rectangle in terms of width and length. So we get to use our W and L. And area of a rectangle is quite simply times length. So nice and easy. And this problem is helpful in that it's going to step out all this process bit by bit. It's not expecting to just figure out the quadratic that we're going to get to on the next slide. More advanced question of the exercise might just give you all this information and say, generate a quadratic and find blah. This is stepping you through how we're going to end up generating the quadratic. Okay. Create a quadratic function by substituting your expression for length. So our expression was 34 take away W, okay, into your expression for area. So, and our expression for area was area equals width times length. So if we substitute all this in where L is, we now get area is equal to W times by 34W. Now if we expand those brackets, we get area is equal to 4W take away W squared, or area is equal to negative W plus 4. We have a W squared. This is now a quadratic. Area of this rectangle that has a perimeter of 68, sorry. Turns out, we now know that its area equal to negative W squared plus 34. Whatever we set W, we get area from it. Decide on a suitable domain. So this, I'm not sure if you have ended up covering it last year, but to go over quickly, domain means the allowable input values. What values can we put in for W? And the hint here is you can't have a negative area or a negative length. So saying that, we also need to think about our initial condition that the whole perimeter is 68. So if we had just one width equal to 68, not going to work. Saying we can't have a width of 100, longer than the whole piece of wire, just a single. The hint here also says is find the W intercepts, which we can consider X intercepts. I might re-explain that because I think I've gone over it a bit quick. Domain is what are the values that we can put in that technically work in this situation. Can I put 100 in for W? No. Can I put in negative 5 for W? No. Why for those? Well, I can't have a negative width, non-existent area, and I can't have a W of 100 because that's longer than the piece of wire. If we think about this as a graph where my x-axis is W and my y-axis is area, so as I change my W, I'm going to get different areas to the shape. So make my rectangle really wide, but not very tall. I'll get one area. As I bring it in, because I've still got 68 worth of perimeter, I could have sort of that shape. I'll have a different area, then I could go the other way like this, and I'm going to have a different area again. And this equation we've come up with, area equals negative W squared plus 34, tells us how area changes as we change our W. So let's factorize it quickly. I'm going to go area is equal to negative bracket w squared minus 34. Actually, no. Okay, I want to find. the w-intercept, so I'm going to let area equal to 0, so I get 0 is equal to negative w squared plus 34. So I say w squared is equal to 34, so w is equal to square root plus or minus square root of 34. Am I missing something? Check. I feel like I'm not getting the right answer. Going. Oh, that's what I've done. There's a w here that I've left off right there. I apologize. Okay, that's going to change how we factorize this. I knew the answer didn't seem right. So we get 0 is equal to w bracket w plus 34. Over here. This w out the front, okay, we could write it exactly the same inside a bracket. And this looks a whole lot more like what we're used to for a factorized quadratic that we can use the null factor law on. So we get, using the null factor law, w is equal to 0, or negative w plus 34 is equal to 0. So we get w equals 0 or 34. So a little sketch. We don't know how high it goes up, but we have something like that, where it goes through 0, goes through 34. So we can say, well, we're not allowed a negative area. Can't have negative this way. We can't go any further this way because we also get a negative area. So the allowable values for w, which is the whole point of this question, was figuring out what are the allowable values of w, is w can be between 0 and 34. Now it can't include 0 because if the width is 0, area is 0. And if it included 34, we tried to say it included 34, well then we would have 34 on one side, 34 on the other side, but that means now our length would have to be 0 and 0 to add up to 68. So, because the length, we'd also get area of 0. So we can't include 0 or 34, but up to. So that's our allowable domain. Finally, a piece of wire, 68 centimeters, blah, blah, all that. What is the maximum area formed by the wire and the dimensions that this occurs? Well, we just found out that area is equal to 34w take away w squared, which rough graph 0 to 34. Well, the turning point, we know, is always halfway between the two intercepts. And the turning point will be the highest point it reaches. That will be our maximum area. So if we find w value, so the turning point w value is halfway between 0 and 34. So that is equal to 17. Yes, is equal to 17. Well, we now know the w value that gives us our maximum area. So, and we know area is equal to 34w. Take w squared, we can substitute that w value in to find our area. So it's equal to by 17 take away 17 squared. Or, actually we'll just try and solve this. We're doing this tech free, so the way we want to go at it. do some multiplication over here at side. 7, 7 is 9. 7, 1, 7. Plus the 4 is 13. There, 1, 7 is 7. 1. Those together we get 9. 309. The 17 squared. Then 34 by 17. 7 4s are 8. 7 3s are 1. Plus 2 is 23. Base. 0. 1 4 is 4. 1 3. Add those together. 8. 3 plus 5. So we get 578. Take away 309. Again, take 3. Do it by hand. 578. 9. 8. 9. 6. 5 take 269. So the maximum area we get is 269, and we're dealing with centimeters in all of this. Centimeters squared. So we now know our width is equal to 17. Our area is going to be 269. The last thing we need, because it says we need the dimension, so we also need to find length. So what does that equal to? Well, we can come back to any of these equations that talk about the connection W and L. So we just have L equals 34 minus W. 34 minus 17. L is equal to that 17 as well. And that's the problem done. That is 17 minutes, so it took a little bit longer than what I wanted. I hope that helps. Let me know how it's going. Exposes you to the ideas. In this case, we had a quadratic that talks about the connection between width and area. We wanted to find out what width gives us the maximum area, and for quadratics, when it's quadratic in this shape, the maximum will always be at the turning point, or if it was the other way around, the minimum would always be at the turning point. So generally these applied quadratic questions have to do minimum and maximum turning points. Sketch a graph. I'll leave you to sketch the graph. There's a whole bunch of CAS active example. This is a CAS active example. So this time they give you the equation, so lots of decimal places, and then you just got to use your CAS. I'll go through in class some techniques that we can do that, either via graphing or using some. That's it, and see you in class.